Right now, something is holding you to the ground. You can't see it. You can't touch it. You can't smell it or hear it. There is no wire, no rope, no hand pushing you down. And yet, you're pinned to the surface of a spinning rock hurtling through space at tens of thousands of kilometers per hour. And you feel completely still. That force has a name. We call it gravity. But here's the question that should genuinely stop you. How do we actually know it exists? We have never seen gravity. We have never touched it. We cannot hold a sample of it in a jar. Every piece of evidence we have for gravity is indirect, observed through its effects on other things. So how did scientists build one of the most precise and powerful theories in the history of science about something they have never directly seen? The story of how humanity discovered gravity is not just a science story. It is a detective story. For most of human history, nobody asked why things fell. Things fell because that was what things did. It was obvious. It needed no explanation. Then came a handful of people who refused to accept obvious answers, who looked at falling apples, orbiting moons, and bending light, and asked not just what was happening, but why. And what they found, layer by layer over 4 centuries, was something far stranger and far more beautiful than anyone had imagined. Let's follow the evidence, step by step, the same way scientists did. Step 1. Things fall at the same rate. In the late 1500s, Galileo Galilei challenged one of the oldest assumptions in science. Ancient thinkers believed heavier objects fell faster than lighter ones. Galileo tested it. He dropped objects of different weights from a height and watched them hit the ground at the same time. The mass of an object didn't change how fast gravity pulled it down. That was the first clue. Whatever gravity was, it didn't care about mass in the way anyone expected. Step 2. The moon is falling. Isaac Newton in the 1600s took that clue and asked a radical question. If an apple falls toward Earth, what about the moon? The moon, Newton realized, wasn't simply floating in space. It was falling toward Earth, constantly, but it was also moving sideways fast enough that as it fell, it kept missing. The curve of its fall matched the curve of Earth beneath it. The moon was in a permanent, endless fall around our planet. This meant gravity wasn't just a local phenomenon. It reached across space. It connected the Earth and the moon across hundreds of thousands of kilometers of nothing. Step 3. Gravity has a formula. Newton didn't just describe gravity. He quantified it. He wrote an equation, the law of universal gravitation, that precisely predicted how strongly any two masses would attract each other based on their mass and the distance between them. And it worked. Everywhere. For planets, for moons, for comets, for falling objects on Earth. The same formula applied anywhere in the universe produced correct predictions with stunning accuracy. That was powerful evidence. An invisible force that behaved according to a precise mathematical law was not a guess. It was a discovery. But there was a problem with Newton's gravity, a deep one. Newton described what gravity did with extraordinary precision, but he never explained what gravity actually was. He admitted it himself. He had no idea how Earth could reach across empty space and pull the moon toward it. He called it action at a distance. And he found it deeply unsatisfying. For 200 years, that question went unanswered. Then in 1915, Albert Einstein proposed something that changed everything. Einstein's general theory of relativity didn't describe gravity as a force at all. Instead, it described gravity as the shape of spacetime. Mass, Einstein showed, curves the fabric of space and time around it. And objects moving through that curved spacetime follow the curves, not because a force is pulling them, but because curved spacetime is the path of least resistance. The apple doesn't fall because Earth is pulling it. The apple falls because Earth has curved the spacetime around it, and the apple is simply following that curve. This was a revolution. Gravity wasn't a mysterious, invisible force reaching across space. It was geometry. It was the shape of the universe itself, responding to the presence of mass. And this new theory made predictions Newton's never could. Einstein predicted that light itself would bend around massive objects. In 1919, during a solar eclipse, astronomers measured the positions of stars near the sun. Their light was bent, exactly as Einstein predicted. Gravity had been confirmed to bend light, something Newton's theory couldn't explain at all. Einstein predicted that time would pass more slowly near massive objects. Today, GPS satellites have to correct for this effect constantly. Without the correction, your navigation would drift by kilometers every day. We know gravity bends time because our technology depends on that knowledge. But here is the twist that makes this story extraordinary. Despite everything, despite Newton's equations, despite Einstein's geometry, despite GPS corrections and bending light, we still don't have a complete theory of gravity. Einstein's general relativity describes gravity with extraordinary precision at large scales. But at the quantum scale, the scale of atoms and subatomic particles, it breaks down. Quantum mechanics and general relativity are incompatible. They cannot both be correct at the smallest scales of reality. This means that our deepest understanding of gravity is still incomplete. Physicists have proposed a particle that might carry the gravitational force, the graviton, but it has never been detected. We do not know if it exists. We have detected gravitational waves, ripples in spacetime caused by massive colliding objects like black holes, confirming that gravity propagates through space like a wave. But what gravity fundamentally is, at the deepest level, remains an open question. Shocking outcome. So here is where we actually stand. We know gravity exists because of what it does. We can measure it with extraordinary precision. We can use it to navigate space, to predict planetary orbits centuries in advance, to detect black holes billions of light years away. But we have never seen gravity directly. We have never touched it. We cannot isolate it, bottle it, or point to a fundamental particle and say, that is gravity. What we have done, what science has done, is build an increasingly detailed map of something we can only observe through its fingerprints. Every object falling to Earth, every planet in its orbit, every beam of light bent by a massive star, every GPS correction made every fraction of a second. All of it is a fingerprint of something we understand deeply in terms of what it does, and still do not fully understand in terms of what it is. Here's the thought that should stay with you. Gravity is the most familiar force in your life. You have felt it every single second of your existence. It has never once let you go, and yet it remains, in the deepest sense, a mystery. We know it exists. We know how it behaves. We know it bends space, slows time, holds galaxies together, and keeps your feet on the ground. But what gravity actually is, at its most fundamental level, is still one of the greatest unsolved questions in all of physics, the most powerful force you will ever feel, and we are still learning what it truly is.